Hello everyone. Hope you're doing well. This video is going to cover some of the spring homework that you did, and I'll quickly go through some of these problems. That are here are pretty good, and then we got to talk about masses oscillating on springs. We're covering it from a work energy point of view only, but this is going to happen again when we do momentum, our next topic. And yeah, just kind of planting the seed now so that you've seen it before. And sorry about that. I just checked a text on my watch in the middle of a video, and I will not edit this because I'm a rude person. I'm very sorry about that. Anyway, back to this. I'm sorry I wasn't there to help you with this, but this is a work energy problem with a elevator that's going to hit a spring. And the trick to this one is, I mean, most people are fine with it. You know, it starts above height 0 with gravitational potential energy. The spring is not compressed in the beginning, but it's compressed in the end, and it's brought to rest. So there's no kinetic energy, no potential energy, but there is spring energy. Here's the issue. If you want to do it right, technically, there's 10 meters before it hits the spring, and then the spring compresses an additional x. So the change in vertical height is technically 10 plus x. And you might be thinking, is that really a big deal? Sometimes it is, sometimes it isn't. But in this case, if you don't do this x, or the 10 plus x, you actually get 1.01. And there's a difference of roughly 5% there. So yeah, I think it's a big deal. And you get a quadratic, which makes it a really nasty, awesome problem. This you can ignore. This is from something else, so we don't want to look at that. But anyway, once you've decided the energies that go on there, that's fine. You got kinetic and potential, and you end with only spring. And you end up with a quadratic because you have an x squared and you have an x. And you get a quadratic for distance. Not a big deal. But in the end, again, kinetic and potential become spring potential. Now this problem here, number 3, you know I didn't draw that. That is directly from an AP multiple FRQ. I'm sorry. I did not create this. So initially, the spring is compressed and it launches across the surface with friction before going off the table as a horizontal projectile. So part 1 is just spring, and then there's a little bit of negative work done by friction, becomes kinetic energy. So 1/2 kx squared. And all right, so this one, clearly this was not done by me. That picture is directly from an AP FRQ. And you are asked for the initial compression of the spring. So this is a spring launching, so work and energy into projectile motion. If you're asked for what's going on in the spring here, odds are you don't want to start there. You want to start with the projectile part and work backwards. It's clearly 2 different topics. Now, in the work here that I started, I did start with spring energy, the negative work done by friction, and you end with kinetic energy. That's all along the table. You don't use energy to analyze the projectile part. The only way you could do that is if you're asked for the speed when it reaches the ground, then you can use energy. But other than that, you don't want to do it. So no kinetic in the beginning, no gravitational potential. Yes, it's above the table, but it never changes height along the table. So just call height 0 the table. And as you can see here, the problem is I'm solving for x, and when I do my work done by friction, technically I don't know the velocity here. So I have to go to my projectile motion. Now at this point, if you don't know what this is, what's wrong with you? We do this all the time. It's horizontal projectiles. Use 1/2 AT squared and 1/2 AT squared. Use the 1/2 AT squared in the y to get the time. Use that time in the 1/2 AT squared in the x to get the velocity. Then you can bring that velocity back up, and then you could solve for delta x. So a 2-part projectile problem working backwards. That's AP. That wasn't even me. This last one's a little ugly because you get a quadratic. But it is moving in the beginning. It's above height 0 in the beginning. And again, I always do this because it's just nice. The spring is initially not even being touched by the mass. There's work done by friction, and then the spring is compressed in the end. The issue here is that there is friction while in contact with the spring. Therefore, the distance over which the friction acts is 1.2 meters plus x. That's the biggest trick to this. And then once you do that, you just do a little bit of algebra, distribute, and you get a quadratic. So that's it for the problems. Hopefully they weren't too bad. Now let's talk about oscillating springs. Oscillating springs, they're right now they're nothing. But I'm trying to plant the seed for what's going to come later. Because when we get to momentum, they definitely like these kind of scenarios. So an oscillating, it's usually a horizontal spring and the mass is oscillating back and forth. Like for example, here's a surface that's frictionless and there's a mass here. This is going to be our equilibrium position. And right now it oscillates. So the next picture, it would be maybe at equilibrium. And then the final picture, it's somewhere over here at amplitude. So this is amplitude. This is also amplitude A. Here is when x equals 0. This is your equilibrium position, x equals 0. All right, let's talk about the energies involved here. So this thing just oscillates back and forth. It gets pushed all the way over here, comes to a stop, and then it oscillates back and forth. Just go wee, all the way home. That was terrible. I'm sorry. In the beginning here, in this first picture, I'm gonna label these pictures 1, 2, and 3, just so we're clear about something afterwards. In this first picture, the x is a maximum. It's at amplitude. That's how much you're compressed. So the spring energy is a maximum. Here, x equals 0. It's at equilibrium, so your spring energy equals 0. Here again, x equals a maximum. It's at amplitude. I should write that here. Amplitude A. Amplitude A. That's your maximum displacement from equilibrium. And therefore, your spring energy is a maximum. When it comes to kinetic energy, here your velocity is 0, so your kinetic energy is 0. Here your velocity is a maximum, so your kinetic energy is a maximum, obviously, 1/mv squared. And here, when you come to the other side, and your farthest point from equilibrium, where you stop and turn around, your velocity is 0, and therefore your kinetic energy is 0. So as you can see, if you look, it kind of oscillates back and forth between, you can see here, there's like maximum spring, 0 kinetic. In the middle, you have all kinetic, no spring. And on the ends, you are back to spring and no kinetic. So it just oscillates, transforming energies from one kind of energy to another. All right, let's say we go from picture 1 to picture 2. From picture 1 to picture 2. In picture 1, all we have is all spring energy. So you just have all spring energy. It's like a maximum. And in picture 2, all you have is kinetic energy, and it is a maximum. That's what we got going on. So this is 1/2 k, careful here, a squared. A is amplitude. That's as far as you're going to get from equilibrium when it comes to a stop and turns around. And that has to equal your 1/2 mv maximum squared, because that'll be your maximum velocity when you cross equilibrium. And the halves will go away. Not that that really matters much, but the halves do go away. And then that's it. I mean, this just says that you're going to start with all spring energy and you're going to end with all kinetic. That's pretty simple. Okay, and you can do the same thing from 2 to 3 or 3 to 2. Either way, you're starting with all of one energy and ending with another. Transformation of energy, that's all. And then what if picture 1 looked like this, where the spring is initially compressed as much as it can be, but then when it gets here, it's there. That doesn't make any sense, does it? When it gets here, it's there. Remember, people, letters of recommendation, they're going to be wonderful. This is not amplitude. It's less than amplitude. So it's still moving to the right. It's got a velocity to the right. But this is some location x. This is where x equals 0, but at some location x. When you see these kind of scenarios, I think it's usually assumed, if I could spell the word usually, nope. Usually, still can't spell it. Usually assumed you start with all spring energy. With all / only, whatever you want to say, spring energy. And I bring that up because I think that's the case for, like, you have to start with all of one type of energy, and it's usually springs. But either way, doing a little math here, this is our initial condition. So it's all spring energy maximum. And then afterwards we're here, but we have both spring and kinetic. Like, we haven't come to a stop, and we're not at x equals 0, so we've got a little bit of both energies. No big deal. So you have 1/2 k a squared is what you start with. You end with 1/2 k x squared, which is less than a, and also kinetic energy. Now, halves can go away if you want, but I'm not trying to solve for anything. I'm just saying we start with all spring, and then we end with both spring and kinetic. From here, you can manipulate math and do some problems. But other than that, peoples, that's about it when it comes to oscillating springs for now. It'll get a lot harder when we get to momentum, but for now, enjoy it while it's nice and easy. Bye-bye.